we have the 1802 Cambridge question. We want to find the infinite series, 1 over 2 plus 1 over 6 plus 1 over 12 plus 1 over 20, and so on like that. Well, to find a series like this, we need to first of all observe the pattern, okay? And then from there, we see if we can maybe use any known tools to figure the series out. Good. Okay, so you observe here that we have 1 over 2, and then the second term is just 1 over 6. The third term is just 1 over 12. Well, I can rewrite this as 1 over 2. 2 is the same thing as 1 times 2, okay? And then I add it with, well, 1 over 6. 6 is the same thing as 2 times 3. So we have this to be 1 over 2 times 3. And then again, 12 is the same thing as 3 times 4. So that will be 1 over 3 times 4. And lastly, okay, which is not the end of the series anyway, this is going to be 1 over 4 times 5. And then we continue like that. So what that tells us is that this is one number, and then we multiply it with the next natural number, and then a natural number we multiply with the next natural number, okay? So to figure out this sum, we can put it down as the sum, okay? Maybe let's use n here. That will be of 1 over n times n plus 1. So you notice that this is 2, then multiply it with 3. This is 3, multiply with 4. 4 multiply with 5, and so on like that, all right? Good. Okay, so as n starts from, well, n is starting from 1 here. The next thing will be 2. So we start from 1, and then we go to infinity, because that's an infinite series. Good. Okay, great. And now, this is a well-known structure. Whenever we have a sequence of that form, okay, we go ahead and resolve it to partial fractions, and that will make everything very easy for us, all right? Good. Okay, so we'll go ahead and resolve this fraction here to partial fractions, and then when we plug back in here, and then we can figure out what this series will be. So since the factors are just linear factors, okay, we are going to have to put them down, just the n, and then we add it with, we put down this other factor, okay, as a denominator, just n plus 1. Since they are all linear, we have to bring a constant at the top, okay, just a constant. Maybe I just use the alphabetical order, A and B. Good. Okay, so our interest is to figure out what this constant will be. Right, good. So I'm going to be using the cover-up method from here, and what we have is that, well, we first of all figure out a number that we can plug to the denominator of A that would make the denominator to be 0. Well, n here will be 0 if n is 0. So that means if n is 0, the denominator of A will be 0. So we come over here, cover up the factor, the n itself, and then plug in that 0 into the other factor. That would be 0 here. We cover it up. We do not look at it, okay? That would mean 1 divided by 0 plus 1, which will just be 1. That will be the value of A. Good. Again, to solve for B, we look at the value of n that will make the denominator of B to be 0. Well, if n is -1, then the denominator there will just be 0. So what we do is to come over here, cover up that factor, which is the n plus 1, substitute the -1 into the other factor. That will become 1 divided by -1, and that will just give us -1 for B. Good. Okay. So this fraction can be composed into the following. A is 1, so maybe I'll just clean A and write 1 there. And then B is -1, so I can clean B and write -1. And notice, since Z was positive, I can put the negative here and then put down the 1 here. Good. Okay, so that means that this series, okay, can now become the sum, as n starts from 1 to infinity, of the two fractions 1 over n minus 1 over n plus 1. Good. Okay, and now that we've got that, that is very nice, okay? Now to figure out what the sum will be, we need to look at a partial sum, okay? By partial sum, we mean we do not want to take the sum from 1 to infinity. Rather, we want to take the sum from 1 to a particular finite number, okay? And then we look at when that number tends to infinity, which will still approximate this series. Good. Okay, so I can look at the partial sum as by putting down A sub m, okay, to be the sum as n starts from 1 to m, right, of 1 over n minus 1 over n plus 1. Good. Now over here, let's observe what that will mean. Well, the sum will mean when n is 1, we are going to have 1 over 1, which is just 1, right? And then we subtract it with, well, when n is 1, that will become 1 over 1 plus 1, that will still be 2. That will become 1 over 2. That will be for the first term when n is 1. Now, when n is 2, we're going to add it with, because of the sum. When n now becomes 2, it will become 1/2 minus 1/3. When n becomes 3, it will be 1/3 minus 1/4. And when n is 4, it will be 1/4, okay, 1 over 4, 1/4 minus 1/5, and then we can continue like that. Good. So that is what we will observe from the partial sum. And now notice that in that case, some things will cancel out, okay? Notice this is 1, it will just be there. The next term is that this minus 2 and this positive 2 will cancel out. The negative 3 and the positive 3 will cancel out the negative 4 and the positive 4, and that is how it will keep, okay, going on until we get to 1 over m minus 1 over m plus 1, which is the last term here, okay, when n becomes m. Good. But notice that this series will keep on cancelling, okay? And there is another term that will cancel out with this 1 over m. What will be left with is 1 minus 1 over m plus 1. So I can put down the sum to be a sub m to be 1 minus 1 over m plus 1. Good. So that is the partial sum. And now, as I said earlier, we want to look at when this n here tends to infinity, all right, in order to get the original sum which we seek for. So as m tends to infinity, we want to look at the limit as m tends to infinity of the partial sum, which will mean the limit as m tends to infinity of 1 minus 1 over m plus 1. Good. Okay, so that would be, well, as m tends to infinity, 1 will just be 1 because that's just a constant, all right? So we put down the 1, and then minus, well, as m tends to infinity, we'll be having 1 over infinity, okay? That will be just be 0 because 1 divided by a very large number, which is bigger than any real number we can compare it with. So that will just give us 0, which means that everything here is 1. So this one tells us that that series, okay, which we seek for originally, is going to add up to just 1. Okay, great. Okay, thanks for watching. Please subscribe to my channel.